Hi everyone, welcome to the third tutorial of a deep learning course. Today we will be looking at activation functions. As you know, activation functions are crucial for neural networks and are basically introducing this nonlinearity in it. If we have no activation functions at all in a neural network, it basically is just a linear function, therefore way less expressive than actually using activation functions. You have seen already in the lecture, there are a lot of different activation functions out there, and all of them might have different benefits and disadvantages. Some work better than others, and we will take a closer look here at why some work better than others and how we can actually identify good activation functions. Again, the tutorial is stored here on our website. If you want to code along, just click here on one of the Open in Colab links, and then it directly opens it in Colab, as I've done here already on this site. Remember also on Colab, we this time definitely want to use the GPU, so go to runtime, change runtime setting, and select the GPU here. It just makes the codes run much faster. In the beginning of the tutorial here, we have again a few standard libraries we want to import, the ones we have already seen in the PyTorch tutorial of the previous one, but also now you see we import here all the different PyTorch packages we have discussed, like torch.nn for building the neural networks, torch.utils.data for the dataset, and torch.optim for our optimizer. So let's start with first importing them, and again say run away anyway, to have the permission here. While this is running, we can already look at the next cell, where we basically define some basic functionality. So we will use here a dataset. We also will have a folder where to save a dataset. We just set it here to random path. Select anyone where you probably, if you run locally, make sure you do it in the same folder as all your other datasets, as otherwise you just have a lot of copies of the datasets on your disk. We will also have here a checkpoint path because we will train models and therefore save some of them. Also define there basically a directory where you can save them. We have here a function now to set a seed for all possible packages we use. So for example, torch, numpy, and also, random we don't use, but usually you also use here random to set the seed to make it deterministic. And also, as we have seen, we set here the device based on CUDA or CPU, depending on what your hardware gives you. And in our case, as we're here on Colab, we should see that the device is a GPU. As the next cell, as I said, we will train models, but training models always take some time. And to reduce this time, especially when you just want to experiment with the notebooks or here that I present them, we have uploaded them to a different GitHub repository, and this cell basically downloads the pre-trained models so you can use them throughout your notebook without the necessity of retraining. But if you want to retrain, feel free to do it. You already see here from the names a few hints what we will do. So we will train different models with different activation functions on a dataset called FashionMNIST, and we'll then compare them in different settings. So let's first start with discussing what are common activation functions and maybe also implementing some of the activation functions by ourselves. So an activation function, as you know, is a very simple operation, or here actually a very simple module in our case. I define here a basic class, a base class, from which we can inherit then all our subclasses, our different activation functions. Just define here a name so we can access it more easily, and we will have here a dictionary called config, which could also be set as, for example, hyperparameters, because some activation functions, as you might know, have different hyperparameters, like the leaky ReLU, for example, has a different negative slope you can change. Therefore, it's also good to just have it defined here, and when we save our model, we will also save this configs. Let's first execute also this cell. The first two activation functions, which are probably the most well-known, or also the basic ones, are sigmoid and tanh. Sigmoid, as you know, takes an input between minus infinity and infinity and maps it between 0 and 1, while tanh maps them between minus 1 and 1. Therefore, sigmoid is often used if you have an output for binary classification, while tanh can be used inside a neural network. We will still also experiment with sigmoid inside the neural network and see what it actually happens if you have it in hidden layers. The implementation is quite simple, so you might already know sigmoid is just 1 divided by 1 plus the exponential of minus x. tanh uses both the exponential of x and the exponential of minus x, so I first calculate them here, and we can then just calculate the tanh down here by the exponential of x minus the exponential of minus x divided by the sum of these two. There are more activation functions, and overall we will look now at 4 more, which you have already seen in the lecture and are also based on probably another very well-known activation function, namely ReLU, so the rectified linear unit. It is very simple. As you know, it just takes basically the maximum of 0 and x, so all the negative values are mapped to 0, and therefore if we implement here in PyTorch, so there are many different ways to implement in PyTorch, and I try just to show a few different ones so you get a feeling what you can actually use. So we could of course just say here maximum between 0 and x, but what you can also say is that we just say x greater 0 dot float and multiply that with x. So that means that this term is actually 1 for all values which are greater than 0, while for values where it's smaller equals 0, it actually sets then also this factor to 0. The leaky ReLU, as you know, has basically is a ReLU, but just on the negative side, it has a small slope, which we use here as an alpha factor. And here we use now the function torch.where, which is also very similar to the NumPy version. There we basically say torch.where, so where x is greater 0, we will use x, and otherwise we will multiply x by our alpha, which we basically stored here, then in the config, so we have a hyperparameter of the activation function. Another one we will look at is ELU. So ELU is basically similar, let's say, to ReLU, but again, in the negative side, we use the exponentially converging to -1 instead of directly setting it to 0. Therefore, we can use here again torch.where, where x is, again, on the positive side, we just use a linear function. On the negative side, we use the exponential of x -1. The last activation function we look at is swish. Swish is a probably quite new activation function compared to the others, because this was found by a large grid search on different activation functions on different data sets. And it has been shown to be one of the best, but in the end, we should still note that this doesn't mean that this activation function is for every possible task and every possible data set, every possible neural network, the best compared to the others. It has nice properties. We will also see when we visualize it. But in general, it's defined by just taking x times torch.sigmoid x. So it basically takes a sigmoid to converge to the 0 output, which is which has nice properties, and we will see it now if we visualize the neural networks, the activation functions. So when we want to visualize them, we want to visualize actually 2 parts. So one part, of course, we want to visualize is if we get now an input, to what output is it mapped? But as you know, as the gradient flow is very important in a neural network, we also want to check how actually the gradient distribution looks like for input values. Therefore, we want to calculate, so for a given input, what is the gradient at this point? In PyTorch, we just do it very easily by using the dynamic computation graph and just do backpropagation. So what I have here is a function getGrads. It takes an activation function and x will be then basically a range between -5 and 5 or so on. And what we first do is we say that this tensor requires gradients. This first operation, clone, means that I basically copy exactly this tensor, but have an independent version, as this requires is then applied in place. We then apply our activation function on the range, so on the x, and we can then just do out.sum.backward, because as you know, if I take a sum, then it basically has in the chain rule, the gradient of 1 to each single input. So it basically is as if I would have called for every single output an independent backward. This is just much faster to actually calculate it. And then in x.grad, I know for every input what is the gradient given this activation function, which is then quite easy to actually implement it. Therefore, then below here, I do nothing else than take all the activation functions and write a bit of code to plot them and also the gradients. So if we visualize it here, we should see very soon plots. Exactly. We, for example, see here the sigmoid. Here's the activation function, which is between 0 and 1. And the gradient, see, for example, as the highest point 0.25. Tan H has a significantly higher gradient. As we already see, this is quite nice because mostly we want to have strong gradients that are neither exploding or vanishing. With a point of 1, it's perfect around 0. ReLU has this characteristic step function in the gradient, while Leaky ReLU has a slightly higher gradient. So it's not 0 at this point, but it's just slightly higher. ELU, as you can see, is basically, instead of also having the step function, we have a small decrease here in the gradient function, whereas Swish is the only of a ReLU family here we looked at that has both a smooth function here, while also actually a smooth gradient. As you can see, because this is not a step function, it is still a smooth function. At the same time, it's also not monotonic, so you can see actually that it changes its gradient sign when it goes down here, which also gives basically another possibility to the neural network to actually learn different features. After now visualizing them, we can start to analyze them by actually training a neural network and checking the activation distribution and gradient distribution.